Okay, so in this example, we're told that the disk of a gyroscope rotates about its own axis at a constant rate of omega 2, and that the gimbal support is rotating at a constant rate of omega 1 about a fixed vertical axis. We're told the observer and the little xyz axes are attached to the disk, and that the capital xyz axes are fixed in space. Given this information, we're asked to find the angular velocity and angular acceleration of the observer at the instant shown. Okay, so to do this, I'm going to start by noting that the angular velocity of the observer, who will be of course attached to and rotating with the disk, will be a superposition of two rotations. It'll be a rotation omega 1, which is about the capital J axis, which is fixed in space, plus a rotation in this case of omega 2 about, in this case, a unit vector little I, which is rotating in space. I'll go ahead and put this in a consistent vector set in a minute, but for now let's go ahead and compute the angular acceleration. So if we do that, taking the angular acceleration of this system, we're going to have omega 1 dot in the capital J, plus omega 1 in the capital J dot, plus omega 2 in the little I, plus omega 2 dot in the little I, plus omega 2 in the little I dot. If we go back to the problem statement here, you'll notice that the rotation rates omega 1 and omega 2 are 0, which indicates that in the angular acceleration the first and third terms will go away. In addition, here you can notice that the capital J axis is fixed in space, so its time derivative will be 0. So the net result here is we get an angular acceleration which is equal to omega 2 times I dot. And we can note at this point that the time derivative of a changing unit vector is given by omega cross itself. So we end up with an expression for alpha that looks something like that. If I substitute in the value for omega given above, we can express this as omega 1 in the capital J plus omega 2 in the little I, cross with the little I direction. Now if we stare at the problem, we note that at this instant in time, or instant in space, the little i's and j's and the capital I's and j's are aligned. Then we can go ahead and put everything in a consistent vector set here and solve for the angular acceleration. So first, let's go back to the angular velocity. We can note that at this instant in time, the axes are aligned, so I can express this all in capital vectors as follows. And then down here below, I can replace the little i's with capital I's at this instant. And if I do so, what I'm going to end up with here is an angular acceleration which is equal to omega 2 times omega 1 times quantity j cross capital I. You'll note the I cross I term goes away here for obvious reasons. If we evaluate this out, j cross I is minus k, and so I'll get an angular acceleration which is minus omega 1 times omega 2 in the capital K direction. From here, all you need to do is substitute numerical values. I know you got it. Best of luck.